Alright, in this video we're going to be looking at 2.3 exponential functions. So we have the general form of an exponential function is given here as f of x equals a times b to the x. Now that looks a little bit different from the exponential form that we're using in our previous lessons. And that, just as a reminder, that exponential form is y equals y sub 1 times our common ratio r to the x minus x sub 1 power. But I want to show you that these two are actually the same thing. So the a that we have here is the initial value of the function. And it's saying where a does not equal 0. We don't want a to be equal to 0. But it is the initial value. And an initial value happens when time equals 0, or x equals 0. So we would have the point 0, comma a. So that would be our x1 and y1. Now we're also told that b is going to be our base or common ratio. It's our base or common ratio, which is going to be a fixed positive number. So we want b to be greater than 1 but not equal to 1. So in this case, b is the value of r, the common ratio that we've been using. So if we go ahead and pull that information, our x1, y1 here, and our common ratio r, then we would have y equals, y1 is a, our common ratio is b, and then we have x minus 0, which really is just a times b to the x. So these are equivalent. All right, so the same exact form, we're just in this exponential form that we have right here. It's a nice form because that a value, again, that is our initial value when t, or when time, or x, or whatever is equal to 0. So we have a lot of different applications in science and economics using our exponential functions, and those include our population growth and decay, money with interest and debt, the market value of cars, houses, devices, and etc. We saw the market value of cars in our previous lesson. Radioactive decay, spread of disease, and more. So we're going to go ahead and use our exponential functions to kind of solve this problem that we have here. So in this one, we have a certain bacterium doubles every hour. So we have that happening every single hour. So it says if you start with 3 bacteria. So I'm going to go ahead and make a table and just kind of see what's happening. So x and y. Our x value is going to be our time in days, and y is going to be the amount of bacteria. So it says we start with 3 bacteria. Now that would be our, again, initial value. And as we said above, initial values happen when x equals 0, when time equals 0. So in this case, at time equals 0, at our starting moment, we haven't started counting time yet for this situation. So that is time, or x equals 0, we have 3 bacteria. But it says that we are doubling every hour. So if we are doubling every hour, well then after 1 hour, how many should we have? Well, 3 times 2 would be 6. So then after 2 hours, how many should we have? Well, 6 times 2 is 12. After 3 hours, how many should we have? Well, 12 times 2 is 24. And it would just keep on going with that pattern of multiplying by 2 every time. Multiplying by 2, multiplying by 2, and so forth. It just keep on going. So they ask, how many would you have after 8 hours? So we could continue with this table that we have here, and we could extend it all the way to 8 hours, which actually wouldn't take us that long, but we also have our exponential form here. So let's go ahead and use that exponential form. F of x equals a times b to the x. So we have that our function has the initial value of 3 bacteria. Our b is going to be that common ratio that we're seeing happening here, that doubling every hour. So b is equal to 2 to the power of x. So we, with this situation, are able to form an exponential equation, which then allows us that after 8 hours, how many do we have? Well, all we need to do is just plug in 8. So f of 8 would be equal to 3 times 2 to the 8th power, which, using my calculator, tells me that that would be 768 bacteria. So there is 768 bacteria after 8 hours. All right, so moving on, we have the next thing we want to look at is what's called the Euler's number. Now this is a popular exponential function that we have, and that is the function e to the x, where e is what we call Euler's number, or the natural number. Either one is fine. They're both mean the same thing. Now, Euler is actually a mathematician. His name is Leonhard Euler. And he lived from 1707 to 1783, and he was a Swiss mathematician and famous for a lot of things in pre-calculus, calculus, engineering, science, lots of different things that he did. And this is just one thing that he is credited for, is kind of formalizing this natural number. Now, it's called a natural number because it actually happens and occurs in nature. But again, we also call it Euler's number because he is the one credited with it. Well, Euler's number is this number here. We denote it with the letter E. So if you ever see E within mathematics now, E is not a variable. It represents a specific number. So it doesn't vary. It represents this very specific number that we see listed here. Now this is irrational. So just like pi, it continues on forever without ending. And it has no pattern. That's what makes it irrational. I can't write this as a fraction. We can get an approximation, but we're not going to get an exact fraction that we can write from this number being irrational. But again, the function e to the x is very popular within our exponential functions. It's used a lot if we come up into applications. It's used a lot for population growth and decay. It's used in interest. It's used in radioactive decay, looking at the spread of disease. So it's used all over the place. So we're going to go ahead and use our calculators to practice evaluating our natural function, our natural number function here, our Euler function, at these different values that I have. Now, we're doing this because we're going to be doing this a lot, so I want to make sure you know where your natural number is on your calculator and how to use it to evaluate different things. So we're going to go ahead and start with x equals -2. I think that should be sufficient for our needs with an example here. So f of -2, in this case that would be e to the -2 power. So I'm going to go ahead and pull up my calculator here. So we have our calculator here, and we're going to go ahead and plug this into our calculator to evaluate what e to the -2 power is. So you want to find your natural number on your calculator. It can, in the TI anyways, it can be found in two different places. We have this one here above the division symbol, but this doesn't have a power. You can use it and then use your caret button to make a power. It works. We also have the e to the x, already with the power over here. And that's above the ln, which is going to be the natural log. So that's actually going to relate the e to the x, and the natural log will relate to each other. We're going to go ahead and use this e to the x. So I go second, and then the natural log button to get e to the x. And then I just input whatever power that I want. In this case, -2. Go ahead and hit enter, and I get 0.135 as the value there. So again, go ahead and do B and C. Go ahead and pause the video and do B and C in the same manner. All right, we're going to go ahead and continue with looking at our growth and decay functions here. So we have growth and decay. So growth, it indicates that a quantity is increasing slowly in the beginning, and then there is rapid increase. We kind of see that with the exponential graph here. This is used to model population growth, compounded interest, finding doubling time, and more. In this case, our function is always increasing. Even if it looks flat here, it is increasing. It just increases very slowly until it hits this part where it starts, shooting up very, very fast. And then the function form would be our general form. A would be greater than 0, but then this is the most important part here, is that our b value is going to be greater than 0. We did actually talk about this in the previous lesson where we had our growth and decay rates, and our b, our rate of the function, rate of growth here, for growth has to be greater than 0. In exponential decay, in this one, our quantity is decreasing rapidly at first and then starts leveling out. The population growth used to model population decay, half-life, and more. This graph is always decreasing. And then we have, again, the form a times b to the x. A is greater than 0, but this is the part, again, I want us to emphasize with exponential decay, in that our b value is going to be between 0 and 1. All right, let's go ahead and move on to the next page. We're going to be graphing exponential functions now. All right, so in graphing exponential functions, we are going to be using our transformations again, our properties of exponents and transformations that we have seen before. And so we have this form, a little bit more involved in this form of the exponential function here, because we are wanting to indicate all the possible transformations. We have our a value that's going to give us our vertical dilation. We have our h value that's going to give us our horizontal shift, and our k value that's going to be giving us our vertical shift there. So the guidelines for graphing that we're going to go ahead and have is that we want to graph parent function, which is just going to be b to the x, so whatever our base is to the x power. And we're going to graph it with its horizontal asymptote. So every single exponential function has a horizontal asymptote, and the parent function is going to be at y equals 0. So we are going to transform the graph as needed, and if there is a vertical shift, remember that to shift the horizontal asymptote as well. So whatever our vertical shift is going to affect the placement of our horizontal asymptote. So we have an example here. This example is y equals 2 to the x plus 1. So our parent function is again just going to be the base to the power of x. So that is our parent function. So I'm going to go ahead and write that in here. Y equals 2 to the x. And its horizontal asymptote, like all parent functions, is at y equals 0. So I'm actually going to start with that horizontal asymptote here at y equals 0. and then we'll see if that gets moved with our transformations. So we're going to go ahead and just do a quick X and Y chart. And in this X and Y chart, we want to go ahead and plot some points. And we're going to do that by plotting just these easy 4 points here, -1, 0, 1, and 2. So I'm going to go ahead and plug this into my function here. So that would be 2 to the -1. And now this is using our property down here of negative exponents, that will become a fraction. So that will become 1/2 or 1/2. 2 to the 0, again using our property that we have down here. 2 to the 0, anything to the 0 power is equal to 1. So I have that one is equal to 1. Then 2 to the first would be equal to 2. And 2 squared would be equal to 4. So I'm going to go ahead and plot those points for my parent function. So -1, 1/2, 0, 1, 1, 2, and 2, 4. So we have this exponential function happening here. All right. So that is, again, our parent function 2 to the x. We want to graph our transformed function, which in this case is y equals 2 to the x plus 1. So we look at this and we see what transformations do we have. Now remember, 2 is the base. That's part of the parent function. So 2 is not a transformation. However, this one is, and hopefully we recognize that as a vertical shift. It's +1, so we're going to be shifting up 1 space. So I'm going to go ahead and take all my points, and they get shifted up 1 space, all of them. Now, in addition to our points getting shifted up, we also have that our horizontal asymptote also gets shifted up 1 space, as so. And so then I have this exponential function going along like this. And that is our function 2 to the x plus 1. Now, that means our horizontal asymptote was y equals 1. Now, I want you to notice something. What was our horizontal shift, and what did our horizontal asymptote end up being? They are the same thing. And that's actually something that's really nice. Our plus k here, our vertical shift, is going to be our horizontal asymptote. If we have a vertical shift, that will be our changed horizontal asymptote. If we don't have a vertical shift, then our horizontal asymptote will remain at y equals 0. All right, so again, some key features to remember of exponential functions. All exponential functions have a horizontal asymptote. That they approach from one side only. So if we were to look at like the end behavior of this function, so the end behavior, we approach this horizontal asymptote on only one side. And so that would be the limit as x approaches -infinity of, and I'll go ahead and just do the 2x plus 1. As I approach -infinity, we approach that horizontal asymptote, so that'd be equal to +1. However, the limit from the right, the limit as we go to the right of our function to the x plus 1 is shooting off and increasing without bound. And so that would definitely be equal to +infinity. So we have a horizontal asymptote on one side and unbounded on the other. And that will always be the case with our exponential functions. Exponential functions are always increasing or always decreasing. Exponential functions do not have any extrema except on a closed interval, meaning we don't have maxes or mins. So this means no max or min. Exponential functions are always concave up or concave down. So if there is no change in concavity, then they have no points of inflection, meaning there is going to be no change in concavity, which again is what we're meaning by either always being concave up or concave down. If we look again at the problem that we have up here, this is definitely a concave up problem. So always concave up. All right, we have our transformations. So we have all of our transformations down here. As a reminder, we have our order of transformations. But let's go ahead and turn the page and try out some of the problems that we have over here. All right, so we are going to go ahead and graph each exponential function. We're going to determine whether the function represents growth or decay. And then we're going to go ahead and state the end behavior of each of the functions using our limit notation. So we are starting with this function here, f of x equals 4 to the negative x. So I always like to start with acknowledging what is my parent function. Well, in this case, our base is 4 to the power of x. So that is our parent function, y equals 4 to the x power. So I'm going to go ahead and just make that table real quick. -1, 0, 1, and 2. And so I have 4 to the -1. As we saw previously, that would be 1/4. 4 to the 0 would be 1. 4 to the first would be 4. And 4 squared would be 16. All right, so we can go ahead and plot these. Remember, parent function, our horizontal asymptote is going to be at 0 automatically. The parent function. Now, if we have a vertical shift, that would change. But do I have a vertical shift? I do not. So that is going to be the horizontal asymptote for my final graph. So I'm going to go ahead and plot these. So -1 and 1/4, 0 and 1, 1 and 4, and then 2 and 16. It's off my graph. So this is my parent function here, coming in really close to my horizontal asymptote, and then shooting off again very, very quickly in that direction. And that is 4 to the x. So we want to go ahead and identify our, so we have f of x is equal to 4 to the negative x. We only have one transformation happening here, and that is this one right here. This is a horizontal dilation, where we're going to go ahead and take all our x values and multiply them by -1, which results in reflecting over the y-axis. So that's the only transformation that we have, so that's the one we go ahead and do. So all our points are going to move across the y-axis. So I have that one there, that one stays put, and that one moves over. And that's the only transformation I have, so I'm going to go ahead and draw my graph. And that would be my graph, 4 to the negative x. Now that's graphing the exponential function. We want to go ahead and determine if it represents growth or decay. Hopefully we can see that our final graph, f of x equals 4 to the negative x, is exponential decay. Now, one thing I mentioned back on the exponential decay, let me go back to that. Right here in our exponential decay, our base or rate has to be between 0 and 1. Well, am I between 0 and 1 on this problem? My base is 4. Is that between 0 and 1? It's not. But it actually is if we manipulate this problem a little bit. So 4 to the negative x is the same as 4 to the -1 to the power of x, which means that that is actually 1/4 to the x. So write it in this form, what is my b? My b is equal to -4, which is between 0 and 1. So we definitely have that exponential decay. So we do want to go ahead and talk about our end behavior real quick. So let's do that. End behavior. Again, this is for our final function, not the original function, but my final function. So we're going to talk about the end behavior from on the left and on the right. So on the left, that would be the limit as x goes to -infinity of our function f of x. Well, looking on the left, where is my function going? It's shooting off definitely to positive infinity. So that would be equal to infinity. Whereas on the right, I have the limit as x approaches positive infinity for my function. And that is going to the horizontal asymptote of 0. So I have my transformations to help me graph. I had that it was exponential decay, and I have my end behavior. All right, I'm going to go ahead and do, let's see. I'm going to go ahead and do C and then D, and leave B for you to go ahead and do. All right, in part C, we have our function here. So what is our parent function? Well, our base is 2, and we just raise that to the power. So 2 to the x, y equals 2 to the x. So x and y chart. Go ahead and still use -1, 0, 1, and 2. We did actually already do this one previously. We'll go ahead and do it again. 2 to the -1 would be 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 squared is 4. Parent function, our horizontal asymptote is at 3, at 0. And let's go ahead and put our points in. So 1/2, -1, 1/2, 0, 1, 1, 2, and 2, 4. All right, so there is my parent function there. So let's go ahead and identify our transformation. So we have f of x equal to 2 to the x plus 1 minus 3. So we have two different transformations here. I have my horizontal shift. Now that's going to be to the left, one space. And then here I have a vertical shift. And that one is going down 3 spaces. So left 1, down 3. So according to my order, this is the one I'm going to do first, and then this one will be second. So all my points I'm going to go ahead and take. I think I can go ahead and do both combined. When I just have 2 shifts, I can do both of them, kind of like slope. I can just do both of them combined. But if it helps you do them separate, you can do that as well. I'll just go ahead and do them separate. So over 1, so left 1, left 1, left 1, and left 1. So that would be my first transformation, which I'll have as dotted here. And then I go ahead and I take each of these points and I'm going to move them down 3 spaces. So down 1, 2, and 3. 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 But again, we also have our horizontal shift that moves down 3 spaces as well. And that is our horizontal or vertical shift. So that -3 that we have here, again, is our horizontal asymptote. That's what it ends up being. And so then that, go ahead and use a different color to represent my final graph here. That would be my final destination for this exponential function, which does actually end up crossing the first one like so. That is our final function f of x. All right, so we have a couple things that we want to look at in that. So f of x, is it exponential growth or decay? And that is definitely going to be growth. We see that from our graph. And also we have our b is equal to 2 there. So we definitely have that exponential growth happening. All right. Let's see. Let's talk about our end behavior here. So end behavior, and that's going to be from the left and from the right. So end behavior on the left. So the limit as x approaches negative infinity of this function f of x. So looking at my f of x function as I go to negative infinity, what value am I approaching? Well, definitely that horizontal asymptote of -3. And on the right, the limit as x approaches positive infinity, well, that's shooting off to infinity, so that's equal to infinity. All right, I'll go ahead and do one more here, problem D, and then that will suffice for these problems. All right, so we have our base to the x, so parent function is definitely going to be 3 to the x. So I have -1, 0, 1, and 2. So that'll be 3 to the -1, or 1/3. 3 to the 0, 1. 3 to the first, 3. And 3 squared is 9. Again, parent function horizontal asymptote is at 0. Does look like I have a vertical shift here, so I'll have my final horizontal asymptote will be at 1. We'll do that when we get to that point. So I have 1/3, 1, 3, and then 9. I believe this goes up to 8. So 9 would be just off the graph there. So there is my parent function. Okay. So let's go ahead and identify our transformations and apply them to our graph. So we have f of x is equal to -3 to the negative x minus 2. Now, we talked about this in our previous transformation unit back in 112. If I have a b value there, I'm going to go ahead and factor that out. So that'd be negative, and then x plus 2, and then plus 1. So I have my different transformations. I have my vertical dilation, where we're going to take all our y values and multiply them by -1. We have a horizontal dilation. We're going to take all our x values and multiply them by -1. We have a horizontal shift. It's plus 2, so that's going to go to the left 2 spaces. And then we have a vertical shift, which is going to be up 1 space. Now, our order, definitely want to do, let's see, remember horizontal dilation, horizontal shift, vertical dilation, and then vertical shift. So let's go ahead and apply our transformations. All right, horizontal dilation, we multiply our x values by -1. That results in a reflection over the y-axis. So -1 times 1 becomes +1. 0 stays 0. +1 becomes -1. And +2 becomes -2. So this is our graph so far. Our first transformation there. And then our second one is going to be our horizontal shift, so all our points move over 2 spaces, 1, 2, 1, 2, 1, 2, and 1, 2. So it'll be right there. So that'll be our next transformation. And then our third one is going to be our vertical dilation. So that is going to be where we multiply the y values by -1, which results in a reflection over the x-axis. So this is +9 here. So that becomes -9 straight down, -9. This one is +3, so that becomes -3. +1, so that becomes -1, and then -1/3. So that is our next transformation. And then the last transformation is our vertical shift, where everything, including the horizontal asymptote, moves up 1 space. So there's my horizontal asymptote up at y = 1, and then all my points move up 1 space. And that is f of x. Now this one, since our a value is a negative, we have that -1a value out front. That actually makes classifying it as growth or decay a little difficult. Let's look back at our definition of growth and decay back on that first page. So growth and decay, on both of them, one thing that it says, a has to be positive. So if a is positive, then we can define growth and decay. But if it's not, then we really can't define it as either growth or decay. So we are going to go ahead and say on this one, since our a value is negative, say since a is less than 0 and is neither growth nor decay. All right. However, we can still do our end behavior. So let's go ahead and do end behavior. So on the left, our limit as x approaches -infinity, to -infinity of our function. To the left, that's shooting down to -infinity. So definitely -infinity there. On the right, the limit as x approaches +infinity of my function should be equal to my horizontal asymptote. As I'm going to the right, I'm equal to my horizontal asymptote of +1. And there we have those 3 problems with our exponential functions. Thank you for watching. Have a fantastic day.